video, we're discussing the probability of at least one, which is a special technique of probability. Probability of at least one problems revolve heavily around the idea of a complement. So let's first get right into that idea. To solve a problem with the probability of at least one statement in it, or at least the idea of the probability of at least one implied in the problem, we have a special formula that's easy to remember because it rhymes like a poem. And that is that the probability of at least one, so the probability of at least one is equal to 1 minus the probability of none. So it's a poem, right? Probability of at least one is equal to 1 minus the probability of none. 1 and none rhyme, that'll help you remember the formula, right? So written out, it's basically the probability of at least 1 is equal to 1 minus the probability of none. That's written out in a neater format. So basically what this is telling us is that the idea of at least one of anything is complementary with the idea of none of that same thing. So for example, if I said the probability that you get at least one A this semester is equal to 1 minus the probability that you get no A's this semester. So that's all you have to do. Whatever follows the phrase at least one, you put down here following the word none, right? So probability of at least one error is equal to 1 minus the probability of no errors, right? So that's all you have to do to fill in the formula. So when do you use it? Well, you can use it any time that the logic of the problem or the wording of the problem implies you're solving a probability of at least one problem. So kind of a classic example of this would be this problem here. In this problem, they don't try to hide at all the fact that it's a probability of at least one. You can see that right away in this last sentence, right? It says find the probability that at least one fails, right? So we're very clear that it's a probability of at least one problem. So let's read the problem. It says, if 5 components in your hard drive must work in order to be able to use your computer, and there is a 1% chance each part fails. So of the 5 parts, for each of those, there's a 1% chance that any of them fail, right? So we want to know the probability the first one would fail at some point is 1%, probably the second one would fail at some point is 1%, so on and so forth, right? Find the probability that at least one fails. So of course, if one of those fails, then your computer hard drive will not work, right? All right, so let's try to figure this out. If we're going to use the idea of a probability of at least one, we have to fill in the formula, just like we saw there. So we'll have, working with the wording in this problem, we'll have the probability. Let's actually write it a little simpler even. Let's just use the notation, right? So we'll say the probability that at least one fails, right? So where am I getting that statement from? Well, right here, right? Find the probability that at least one fails. That's all I'm doing. I'm looking for find the probability that at least one fails. That's all I'm interested in, right? So I'm writing it down just as I read it to you. Now, if you look at the structure of the formula I had before on the board, everything here is the same except for I added the word fails. So that means for the answer I have to do 1 minus the probability that none fail. And that's it. That's all I have to do. That's how the formula works. Now, the reason why the formula is necessary is because there are lots of ways that at least one could fail. You could have one fail, or perhaps 2 fail, or perhaps 3 components fail, or perhaps 4 components fail, or perhaps all 5 fail. Each one of those is its own separate probability problem, and then we'd have to add all those results together. So that's 5 unique problems that have to be added together, and each of those problems in and themselves is pretty complicated as well. So this is a much faster way because there's only one way that none of them fail. If you think about it, think about the scenario. How do we have it not happen, right? How does it not happen? You know, at least one fails covers all the possibilities. 1 fails, 2 fails, 3 fails, 4 fails, 5 fails, right? The only time it isn't true is if none of them fail. So basically, if we take from the 100% of possibilities that exist, the probability that none of them fail on you, you'll be left with all the other possibilities, which is the probability that at least one of them fails. Okay, so whether you understand the logic fully or not, this technique will always work when you have a problem that says probability of at least one, right? So at least one, you just do 1 minus probability that none fail in this case. All right, so now that we know what we're looking for, the number 1 is just a constant, right? So we don't have to do much with that. We just put the number 1 there. But now we have to figure out this, the probability that none of them fail. So in order to figure that out, we're going to have to say, okay, well, you know, what's involved in this problem? How many steps are there? How many events are there? Well, there are 5 components, right? So there's essentially 5 events, and we want none of them to fail. So when the electricity runs to the hard drive, for example, we want the first component to work, we want the second component to work, we want the third to work, the fourth to work, the fifth to work. That's 5 events. So that means we're dealing with a multiplication rule of probability. Now I'm going to multiply those 5 probabilities together that represent the 5 separate events. And what are the events again? Well, it's the probability that the first event is successful, times the second event is successful, the third, the fourth, and the fifth. When we say successful here, we mean that the thing actually works because we don't want any of them to fail. So in other words, when I look at this first component in the hard drive, what's the probability that it doesn't fail? What's the probability that it does not fail? Well, there's a 1% chance it fails, so it must be a what? A 99% chance that it works, right? There's a 1% chance it fails, there's a 99% chance that it doesn't fail. So that's the probability that it works or it does not fail, so 0.99. Now the next component, assuming it operates independent of the first component, would also have a 99% chance of working correctly, and then 99% chance for the third, 99% chance for the fourth, 99% chance for the fifth. Remember, we want all the components to work. So that's basically your answer. It's 1 minus 0.99 to the 5th power. All right, and when we work that out, we'll see that the answer is 1 minus 0.99 to the 5th power. We get the solution 0.049. 0.049. So 0.049 turns out to be the answer. So almost 5%.